But there are experiments that explore related ideas, particularly the idea that time is relational.
Relational, meaning it depends on relationships between things.
Yes, including the relationship between a system and an observer. Imagine a simplified lab setup. You have two quantum systems. Let's say one acts as a basic clock. Maybe its quantum state changes predictably, like flipping back and forth.
Oh, a quantum clock.
And the other quantum system evolves. Its state changes based on the ticking of that quantum clock. They're interacting.
Got it. Clock and evolving system.
Now, here's the key part. Imagine an internal observer. Someone or something inside this combined system interacting with both parts, seeing the clock tick and seeing the other system change accordingly.
What would they experience?
To them, time would appear to flow normally. They'd see a clear sequence of events. Clock ticks, system changes. Clock ticks again, system changes more. A before and an after, just like our everyday experience.
Okay, makes sense. But what about someone outside?
Now imagine an external observer, someone looking at the entire setup clock plus evolving system as one single isolated quantum entity.
From the outside looking in.
Right. If that whole system is treated quantum mechanically, especially if it's in what's called a superposition of energy states, then from the outside, there might be no apparent time evolution at all.
No time passing.
The external observer might just see a static, unchanging quantum state, a state where the clock and the system are linked, entangled, but nothing is happening sequentially. The whole thing looks frozen, just like the Wheeler-DeWitt equation suggests for the universe.
Is this just theoretical, or has someone actually done this?
Well, there was a fascinating experiment back in 2013 in Italy that provided some really intriguing preliminary evidence along these lines.
Tell me more.
Researchers used entangled photons, particles of light. They essentially set up one part of the entangled system to act as a clock by manipulating its polarization state, and the other part as the evolving system. Then, crucially, they looked at the evolving system from two viewpoints. First, internally, by correlating its state with the clock state. Second, externally, by looking at the quantum state of the whole combined entangled system.
And what did they find?
Exactly what we just discussed. The internal view, correlating the parts, showed a temporal evolution, things changing over time relative to the clock. But the external view, looking at the total state, it appeared static, unchanging. Time seemed to disappear from that global perspective.
Wow. So time depended on whether you were inside or outside the system.
That's what the experiment suggested. The crucial insight here, connecting back to the emergent idea, is that maybe our experience of time flowing is intrinsically linked to us being part of the universe, interacting within it.
Not looking at it from some impossible outside view.
Exactly. If you could somehow see the whole universe's quantum state from outside, maybe it would look static and timeless.
That has really profound implications, doesn't it? It suggests time might not be universal in the way we assume.
It really does. Maybe time only exists, or is only meaningful, from within systems where change and observation are happening. It ties the existence of time to interaction and perspective.
It blurs the line between the observer and the phenomenon itself.
Which is, of course, a recurring theme in quantum mechanics.